Hi, this lecture is meant to introduce you to the Schrodinger equation. The Schrodinger equation is sort of the central it's the central piece of physics that is quantum mechanics. At least, honestly, it's non-relativistic quantum mechanics. So quantum mechanics tends to be introduced for the cases of particles traveling much slower than the speed of light and having non-relativistic energies, so just small energies. Yeah, so anyways, so this video is meant to introduce you to the Schrodinger equation. So the Schrodinger equation, remember the person's name really has this umlaut on top. This up here, let me put it in red, is the Schrodinger equation. So what's interesting about this is I have an equivalence where everything on the left-hand side is sort of spatial things. So I've got this spatial function called u of x, and over here I've got this spatial derivative in the x direction. It's actually a double derivative, and they're acting on, in a sense, the wave function psi, which is actually a function of both space and time. And then on the right-hand side is a time operation. It's a time derivative on the same wave function psi of space and time. And then besides that, it's got this IH bar, and it's got the h bar squared, and there is a division by 2m. This thing is a differential equation. It's an equation because there's an equal sign, and it's differential because I have a double space derivative over here and a time derivative over here, and you'll notice that they're all partial derivatives, right? Partial derivatives. Okay. So the Schrodinger equation is this differential equation, and it's going to have different forms depending on the system that you are modeling. So for example, up here, this function u of x that sits in Schrodinger's equation, this is part of what you're modeling. So we could, for example, and we will, right, a little bit later in this, I think it's, yeah, just it's just a few lectures from here. But we could say, put in details that cause us to consider a particle of mass m stuck inside of a box. So u of x expresses the box. In a sense, u of x tells us about force, and also it tells us about it. The best way to think of it is as potential energy, right? And really quickly, potential energy, you can see that it's a function of space. Remember that there is a force associated with that potential energy because of the negative derivative of the potential with respect to x, right? This is the x direction force associated with this potential, right? Remember that force and potential energy are related. In fact, force is the derivative of the potential energy with a minus sign, right? So some of the input into Schrodinger's equation is what forces is my particle, my quantum mechanical particle, like what forces is that particle going to feel? And we put all the details about those forces into this function called the potential energy. And that potential energy takes a really important position in the Schrodinger equation, because this potential energy with this derivative in the rest of the differential equation is going to give us the wave functions. So the wave functions depend in this differential equation way, the wave functions themselves, which express the probability, right? They're dictated by the forces in our particle model, our model that describes how the particle's being pushed around. We could do particle in a box. A little bit later, we'll also do the harmonic oscillator. And a little bit later, we could even study the hydrogen atom. And the way we'll do that is we'll say that the potential energies associated with the Coulomb interaction, right? The Coulomb force, right? We could also set u of x equals to 0, and this is an example of a free particle, which I described in a couple of previous lectures, right? So if u of x is equal to 0, you just go up in here and you set u of x equals to 0. So there is no, it'll be 0 times, the wave function, which is overall 0. And we've got negative h bar squared over 2m, two space derivatives of this wave function psi of xt equals ih bar, one time derivative of the wave function in position in time. Okay, so you know that, so from the time, so this is a differential equation. Yeah, no big deal. So the answers to the differential equation are called the wave functions. And you notice that the wave functions are space and time dependent, right? So the differential equation itself is derivatives in space and time. So the wave functions are going to be functions of space and time. Yeah, okay, so let's move down. I guess I erased some of the stuff down there, but so let me rewrite, because I've kind of messed up everything up there. So we've got, so I'm going to rewrite Schrodinger's equation. So minus h bar squared over 2m. The minus sign's important. The h bar squared's important. The divide by 2m is important. I've got a double space derivative, partial derivative, on the wave function. And then there's a plus u of x. So this is a plus sign compared to this minus sign. And this just simply multiplies the psi, the wave function. And this is equal to, and here's another important choice of sign. Do you notice there's a plus sign right there on the time derivative? So it's really important, right, that there is an ih bar. There's no minus sign on the right-hand side, the time derivative part. So it goes d by dt of psi, x and t, and I've been dropping the dependence. So let me just continue to drop it. Okay, and you notice that I've been trying to keep this like style of putting these are called serifs, these little toppers, right? Because this psi is actually a function of space and time. And this is opposed to the time independent psi of x. So here's something really interesting that you can do. So when the potential energy function, which in general actually can be a function of space and time, you can imagine a force that changes in time, right? But let's say that our forces, that our little particle of mass m is under the influence of, let's say that the forces are actually fixed. That is, they're only dependent upon space. So whenever the potential energy has no time dependence, it turns out that this wave function, which is a function of space and time, can be rewritten in a really interesting way. It can be written this way instead. The time independent part multiplied by simple multiplication E, actually let me look really quick because people define it slightly different depending on who you're talking to. It's e to the minus I omega t. Yep. Cool. So only in the cases, right? So when the potential energy is actually not time dependent, right? Whenever that's true, the wave function, which is the space and time wave function, is so-called separable, right? So a separable solution. I've got a space part separated from a time part, like this. All right. Yeah, I'm gonna stop there and then move on into another video and have a couple of examples. Or actually, sorry, I'm not gonna stop there. Just a second. There was something I wanted to do. So recall the momentum operator. The momentum operator, p sub x, so this is not a number, it's actually an operation. And the operation is minus I h bar d by dx, right? It's an operator. So you've got to actually cause the derivative to happen, right? So recall the momentum operator. If I want the momentum operator squared, right, I just do minus I h bar d by dx, and I imagine using it after minus I h bar d by dx has already happened, right? So it's going to operate on something that sits over here, some sort of function, and it's often the wave function psi that sits there. But let's just study the operator by itself. So minus I h bar times minus I h bar, right? The minus sign and the minus signs, they cancel, but the I gets squared to a third minus sign. So 3 minus signs is left over as 1 minus sign, and I've got h bar squared, right? And then d squared by dx squared, like this. So if I was to take p sub x squared and divide by 2m, what I'm going to get is minus h bar squared over 2m d squared by dx squared. And this thing that's right here, this is kinetic energy. And that kinetic energy is what sits in front right here. So this right here is a kinetic energy term. This right here is a potential energy term. And this over here, right, if you imagine adding the kinetic energy and the potential energy, this is the total energy. And this is the total energy term, right, of a system, essentially of one particle subject to this potential energy, to those forces. And this is the interpretation that the Schrodinger equation is an energy statement. And that's the sense in which you model your problem. You say that my particle is a little system whose energy is designated this way. And this is the quantization of the model to write down the energy statement, right? The energy model of your particle, which is sort of a classical idea. And then the quantization is to imagine the kinetic energy as actually this operator on the wave function. The potential energy is just a multiplicative operator on the wave function. And the total energy is a time derivative operator on our wave function. And the wave functions are associated with probability, right? And this is what quantum mechanics is.